Okay. So I think we are ready to go. And yeah. Okay, perfect. So good afternoon, everyone. It's a great pleasure to kick off our seminar series for spring with our own Jason Eshraghian, Assistant Professor in Electrical and Computer Engineering. As you probably know, he does a lot of work on what's called brain-inspired computing, and today he's going to tell us quite a bit about what he's been doing recently on language models. But I wanted to tell you a little bit about Jason. Jason came to Santa Cruz a few years back after receiving a PhD in something somewhat different.
Just ask ChatGPT.
I'm going to let you tell us about that. But he received a PhD from University of Western Australia. Am I correct? In 2018. And then he was a postdoc research fellow at the University of Michigan in Ann Arbor. And we were very happy to have him here. I think anybody will escape Ann Arbor, right, for Santa Cruz. But I think this is a great arrangement. And he's currently also serving as the Secretary of the Neural Systems and Applications Steering Committee. He's an Associate Editor for APL Machine Learning. He also has received a number of recent Young Awards and also very important awards that only senior people receive in the area of circuits and systems. He's a fellow lecturer for IEEE Circuits Society, I believe. And he has a lot of energy. And I thought that today we will hear and pay attention to some of the, I would say, the new directions of circuits and algorithms. So, Jason,
great.
It's yours.
Thanks, Ricard. I thought I gave you a 2-line bio where I was far more sarcastic. I guess you went for the extended version. Awesome. Let's just get stuck into it. We're going to talk about low power language models. Why do we care about low power language models? Well, if I pull open my grant writing machine for me and I go ahead and ask it, how much did it cost to train you? And granted, this is an older version of ChatGPT. And it's going to do what every professor is very good at, and that is answer all the questions that I didn't ask it. It's going to talk for a very long time, expending energy to generate every word, every token, to tell me the information that I don't want to know. And to be fair, this is proprietary information. What we do know is that the latest iterations of ChatGPT cost on the order of $100 million to train, just in terms of energy budgets, before you even start spending money on engineers. Okay. On the other hand, maybe I want to know how much does the brain cost in terms of watts. Right. And this time I want it to be as succinct as possible. And it's going to tell me that it takes about 20 watts of power, the same amount of energy to run a tungsten light bulb. And I'm able to talk. I'm able to generate language and thoughts and get creative far, far, far more efficiently than ChatGPT ever could. To be fair, ChatGPT can do an incredible amount of things that I am incapable of, but this energy discrepancy is really what we're trying to bridge, right? So 20 watts. And a big reason as to why that is the case and why the brain is so much more efficient is because our neurons, our brains have learned how to communicate and how to process information in a highly, highly efficient mode of representation. And that mode of representation is known as a spike, right? What is a spike, right? Evolution sort of discovered of its own volition that given a set of ion channels, given a set of biological matter, something called a spike is the most optimal way to transmit information from neuron to neuron. So let's try and get a sense as to what the 3 S's are and how we can take inspiration from them. So firstly, spike. So what is a spike? It's the mode of communication between neurons. And so if I take this cartoon depiction of a neuron and I take an electrode and I stick that electrode into this wire, the output wire, the axon, then for the most part, I will actually sense nothing, right? There will be nothing to sense. There will be a steady state voltage and it's going to be static. But then if this neuron is sufficiently excited, then I'm going to see this voltage perturbation. That voltage perturbation is on the order of 70 to 100 millivolts. But that voltage perturbation is what we typically refer to as a spike or an action potential. The thing is that a lot of neurobiologists and neuroscientists don't really care about the pulse width or the amplitude of this voltage burst. They just care that the spike happened, right? And the reason for that is because most spikes look very similar. There are very subtle differences between them, but we don't really think there's too much meaning imbued in the shape of the action potential. We just care about whether or not it happened. And whether or not something happened can be very simply represented by a stream of zeros and ones, right? Binary events. If there is no spike, treat that as a zero. If there is a spike, treat that as a one. Why is that useful to us? Why do we want to have this 0-1 representation? It's that if I was to take a large-scale neural network with billions or trillions of parameters, and then I'm suddenly telling you that each one of my neurons are very quiet, right? They're transmitting zeros, or they're transmitting nothing, rather. Then that is to say that that neuron, with its many zeros, every time it triggers an output zero, that zero is going to be accessing a bunch of values, a bunch of weights. That value is multiplied by billions of weights. So what I'm saying is that if you have 0 times any other number, that's just 0. I don't need to execute that operation. I don't need to access the weight. I don't need to go off chip to memory, to DDR, to wherever, because I already know the outcome of the answer. The moment I see 0, I know my output is 0. I know any operation, downstream operation, will be 0. And so really, it's the sparsity that we care about, right? So in a way, you're able to reduce the amount of energy expended in going from processor to memory, right? So skip the operations that you can already kind of speculate. And so sparsity is our second S, and biological neurons are actually incredibly quiet, right? Microprocessors might be operating at 2 to 3 gigahertz, but biological neurons, where do they sit? 0.1 to 10 hertz. Biological neurons are incredibly quiet and much, much slower than computers. So if I can really hone in on why this matters, if I give you this list of numbers, 0, 0, 0, blah, 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 7, 0, 0, blah, 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 5, that's all fine, but I very much wasted my breath explaining that list. It would make a lot more sense for me to just say I have a 7 at position 10, 5 at position 20, right? So in a way, I'm only adding to memory every time I have a non-zero element, okay? So we're seeing kind of a duality of benefits as a result of sparsity. We're seeing sparse communication, right? I can reduce the amount of times I go to memory and execute an operation in that first benefit. And the second benefit, that comes about when you're kind of caching information. If you have a stream of zeros, don't store them. Just store information. If you have enough sparsity, then it makes a lot more sense to only store non-zero elements. And then finally, we're not going to really look at this in too much detail, but the third S or third and fourth S's, it's just this idea of static suppression. And that is that the sensory periphery and humans in general, we don't really pay attention to things unless there's some sort of delta, unless there's some sort of change, right? Every time I change my slides, you look at the screen. Every time I wave my arms around, you look at that. But if I told you if I asked the question of what's in the top left-hand side of the whiteboard behind me, you probably wouldn't know until you looked at the whiteboard itself, right? So you're only really looking for change in salient features of interest. So all of these things kind of come together in order to really help humans lower the energy usage in doing all of these incredible cognitive tasks, right? So with that being said, how can we actually make this useful? And so one abstraction of biological neuron models is the leaky integrating fine neuron. Very simple. You can kind of think of it as this node where if I stimulate it with a bunch of input spikes or input current injection, we've got a bit of latency here, that's fine. If it's sufficiently excited, only then does it trigger its own output spike, right? And in absence of that excitation, then it's just a bunch of zeros, or there's nothing to process, right? If we're dealing with spikes now, what we really might care about is when the spike occurred, or how many spikes there are, or the sequence of spikes. There's all of these kind of temporal aspects to it now, right? Let's dig into this a little bit deeper. So what dictates the dynamics of this neuron? Very simple. First order ODE, right? So if I trigger an input spike, some sort of input current injection to this neuron, then there's going to be a membrane potential difference, a voltage difference between the inside and outside of this neuron. So we see this represented by this jump upwards. And then in absence of any input excitation, then we see exponential relaxation back down to a steady state value. Here, we've just normalized everything to 0. In biology, that would look something more like negative 70 millivolts. But then, here we see a leakage, right? That comes from a capacitive charge decay effect. That's where the leak comes from. And then you can see a spike train, right? In response to that spike train, your membrane potential starts to kind of ride on top of itself. You get some sort of accumulation or integration. That's where the integrate comes from. Now, if that membrane potential is sufficiently high, then it triggers a spike. You reach some hard threshold, In biology, this is a little bit more complex. It's more of like an adaptive threshold, but here in this picture, I'm just saying, cool, let's just set our threshold to 1. I don't care too much about the exact numbers. I just want the dynamics to look similar. That membrane potential reaches a threshold, get a spike, and only then is information going to be transmitted from this neuron to all downstream neurons. And in modern computing, it's communication of information that is the dominant cost. 2 times 2 is very simple in hardware. 2 million times 2 million, it's also very simple in hardware. It's the transmission of the 2 million that is expensive, right? So that is really what we're trying to address by using spiking neural nets. And so what I've got pictured here is just an alternative way to represent everything you saw on the previous slide, just discretized over time. So imagine I have a current injection at some discrete time step, p equals 0. That contributes to my membrane potential. And then I check whether or not that membrane potential exceeds the threshold in order to either generate a spike, 1 or a 0. Then we move forward 1 step. That membrane potential gets decayed by a factor of beta. And if beta was, say, 0.5, that's just effectively telling you that the membrane potential will decay by a factor of 0.5 at every time step, which is effectively exponential relaxation, tending towards 0. So this is an unrolled computational graph. It's acyclic, which is convenient because what else is an acyclic computational graph? Neural networks, right? And so this kind of question arises of how do we train a neural network? Error backpropagation. Everyone applies gradient descent and just backpropagates through this graph in order to optimize some parameter, W. In reality, you've got millions upon millions of these, though. But then what if we have a time-varying neuron? Well, deep learning kind of address that as well. You backpropagate your errors through time. You iteratively apply the chain rule again and again, optimizing all of your weights. And just for context, this is just 1 neuron simulated for 1, 2, 3, 4 columns, 4 time steps. In practice, you're going to have many more time steps, many more neurons. Modern neural networks have 1 trillion of these W values, right? So this is all really happening at a very, very large scale in order to do useful things. So that's all well and good. There's a whole lot more I could say on training spiking neural nets. Not going to do that. I just want to kind of dig into the applications and find something interesting there. But what we did was we came up with all these techniques. We made it very accessible. We made it mind-numbingly simple to train these models. And back in 2019, I started this project, started developing SNN Torch, a Python library for training spiking neural nets and making it far, far simpler using gradient descent. It enables a bunch of interesting features like real-time online learning. It works very seamlessly with PyTorch, and it's had a couple of downloads, so that's pretty cool. And it's also compatible and effectively compile onto low power and what we call neuromorphic brain-inspired hardware. And that brain-inspired hardware is really quite optimized for sparsity. So if you have neurons that are not transmitting information, then it knows that. It knows not to compute on those zeros. If I run an SNN, if I run a spiking neural network on a GPU, those zeros are still processed. So we don't see these same benefits on a GPU as we would on custom, bespoke, asynchronous hardware. So just for context, you don't get performance gains by virtue of using spiking neural nets. You need to have the hardware that is optimized for that algorithm, right? That's a big part of what my lab does. We go for the software, we dabble with the hardware as well, because you kind of need to co-design these things. And a couple of cool places are using it as well. NASA in particular is very cool because they're kind of pointing cameras up into space. And you know what's in space? A lot of nothing, right? So why process pixels that are dark when you don't need to? Spiking neural nets are a very natural fit for that. I've also developed it's effectively what I consider a dynamic online living and breathing textbook with code that you can interact with, all in Python, PyTorch, SNN Torch, that really gives you a low-level, detailed understanding of all of these things. So if you are interested, I would recommend checking that out. So how do we work with SNNs? Now, the reality is that for the most part, spiking neural nets have kind of been considered as a bit of a toy neural net. It is very difficult to make them do functionally useful tasks that compete with modern deep learning. ChatGPT is incredible. Modern language models it's insane what people have been able to do with deep learning. And spiking neural nets, if your output activations are 1 and 0, you're losing a lot of information, right? I've been telling you that the goal is to project information over time instead. But we still haven't quite cracked that. We don't know what the neural code is. We don't know how the brain works. So it is a very challenging thing to make these two things compete with one another. We've got energy efficiency, but at a loss. So when one of my first PhD students, Regia, he joined my lab, we immediately started working on kind of breaking that, trying to make SNNs compete with large-scale models. So language modeling in particular was, of course, the obvious first choice. So we worked together on SpikeGPT, the largest spike neural net trained by a backprop in the first to perform language generation. So well and good. There's a bunch of text samples here, which you don't need to worry too much about, but it generates pretty functional text, which was really impressive for a spiking neural net at the time. Now, this isn't very impressive. We've seen ChatGPT, we've seen text generation. So, the field moves incredibly fast. What was nice, though, was that we were able to achieve 30 times less operations thanks to sparsity than a modern language model, a transformer-based language model of equal size. So the question I have is, why isn't the world using it then? Forgive the formatting, right? Why isn't the world using SNNs? If they're all there, if all of this is so incredible and we're getting more energy efficiency out of it, well, the reality is that scaling hurts. When we released SpikeGPT, that was a 216 million parameter model. And that alone was the largest scale model that existed for a spiking neural net at the time, using gradient descent, that is. What is the size of GPT-4o? How many parameters are there in the latest and greatest and largest language models? On the order of 1 trillion. We are lagging behind by a factor of 10,000 parameters, right? Now, when we took SpikeGPT and we scaled it up by 10x to 1 billion parameters, we still got it to work, which was really nice. But the performance improvement was marginal. It was not worth the extra time we spent training that model. So it was a little bit disheartening. I mean, that all the work that we're doing is meaningless. Fingers crossed, no, but maybe we just have to kind of realign ourselves in order to make the right tool apply to the right task. So we flip things on their head. We learned a lot from building SpikeGPT. We moved away from activation sparsity, that is, neurons are sparsely activated, and instead we looked at kind of weight sparsity. So the parameters themselves are now ternarized, that is, every weight is constrained to being -1, 0, +1. So we managed to elicit a lot of weight sparsity from the zeros, but -1s and 1s are very easy to work with. And it's this matrix multiply-free language model. This one scaled incredibly well. We managed to train something 2.7 billion parameters, and it worked really nicely. So firstly, using ternary parameters, you're suddenly using 8 to 10x less memory than something 16-bit half precision or brain flow precision. Then, of course, something's got to give, right? You're removing some information. So, of course, performance degrades a little bit. But we kept in line with using this kind of time-varying sequence-based model. So spiking neural nets, they're all about time. They're all about sequences. It's a dynamical system, right? The SMATMOL-free language model, likewise, also a dynamical system, something varying over time. One of the challenges with time-varying models is that when you make the Markovian assumption that everything in your present state is fully dependent on your previous state, and you don't store a full history of everything that's ever happened, then you're effectively doing a whole heap of compression. You're compressing everything that's ever happened to you within a vector. The challenge with that is that you lose information. If I want to throw a PDF at ChatGPT, if ChatGPT was trying to compress that PDF in the way that I'm describing, then it's going to forget everything at the start of the textbook, right? And spiking neural nets and brains are alike. We as humans are very susceptible to forgetting things from not even a while ago. I don't remember what I had for lunch yesterday. So one of the key innovations in MATMOL-free was effectively learning how to forget, right? If you are memory constrained, if you have a fixed vector size and you can't expand your memory context, how about you use another neural network to dictate what to get rid of? And we'll look at that in a bit more detail shortly. And most critically, we effectively were able to reach 13 watts at human readable throughput. The brain was 20 watts. So we're doing something right there. So let's dig a little bit deeper into what it is that we did. Let's take this toy sentence example. Shrek saw Taylor with binoculars. And my question to you is, who has the binoculars? Is it Shrek? Is it Taylor? Right? So take a moment. Linguistically speaking, it's ambiguous, right? I have not specified this sentence in a way that lets you with certainty ascertain whether Shrek or Taylor have the binoculars. I don't know what, but then with a bit of context, we can appreciate that Shrek saw somebody else. Therefore, Shrek probably saw Taylor using his own binoculars for whatever nefarious purposes that Shrek may have. So if I was to pass this through a language model, a modern language model, not one about, cool and sexy and fancy spiking neural nets or whatever, what would happen is Shrek, or at least little subcomponents of the word Shrek, would be vectorized and represented using a bunch of numbers. Every word is being represented as a list of numbers. They go through a whole series of nonlinear operations. Finally, you end up with this matrix. And this is a self-attention matrix where every word has kind of like a value that represents how tightly it's related to every other word. I'm being a bit sizzling. I'm being a bit abstract and hand-wavy here. In reality, you're going to get latent and abstract representations of sub-pieces of word and then, culminate a bunch of context to kind of support words. So it's a bit more complex than what I'm making it out to be, but I think the intuition is here. In this self-attention matrix, I'm implying with this red that I have a high value. Now, if I say that I have a high value here, then there's a tight relationship between Shrek and binoculars. Taylor and binoculars also has some lighting up, but it's not as strong as Shrek and binoculars. And so self-attention has the ability to recall every single vector. Every time I add another word, I get another vector. So in a way, you're just blowing up your memory quadratically because one extra word extends your x-axis and your y-axis. So you have quadratic memory scaling. And if you have matrix-matrix multiplication, that's cubic complexity, which is not ideal. We don't want that, and brains don't do that at all. But the point is that it works really well because you're storing every single bit of information known to mankind, right? So memory grows quadratically with increasing sequence length. And your brains are not undergoing neurogenesis with every word I say. You do not instantiate a new neuron. You do not allocate new space and invent new fucking memories, right? It's not like that, right? Otherwise, our brains would heat up and thermally just melt, right? So how can we kind of bridge this? The problem is if I use a time-varying model with limited memory, then I run into this problem. Other than the problem of formatting, then by the time I kind of sequentially pass every word one at a time to a model, then by the time I reach the final word, binoculars, I run the risk of all information about Shrek kind of being replaced by Taylor. And if I can just show it to you in a more quantifiable manner, remember that spiking neuron example? Let's imagine this first current pulse is representing Shrek somehow, being a bit arbitrary. But by the time we've reached the end of the sentence, all information about Shrek has faded away. That is actually why people moved completely away from recurrent networks of temporal and sequential models in favor of self-attention. So what that is to say is that attention has too much information with its quadratic memory scale. But damn, it works really fucking well, right? Spiking neural nets and more generally, recurrent neural networks, they don't have enough information. But damn, they're cheap, right? How can we bring the best of both worlds together? That's the goal. In order to kind of realize this goal, my brilliant students and myself, we kind of came together and we thought, what is it about transformers that really makes them tick? What are the pieces of self-attention? Self-attention being the backbone of modern language models. You can distill all of the papers out there, a horrific number of papers on arXiv and NeurIPS and all the fancy ML conferences. They all had 4 pieces in common. 1, token mixing. Token mixing just refers to the idea that you have a spread of information and you mix them, right? Words are represented as sub-pieces or tokens, and you're effectively just mixing information over a sequence, over time, over a PDF. Then you have channel mixing. That is, your neural network itself has a bunch of parameters. And when I flood that network with other vectors, with tokens, then I'm mixing that vector with a bunch of pre-saved information. So if ChatGPT has compressed the entire internet's worth of information, that's the channel. And I'm mixing incoming information with the internet in a way, right? So that's channel mix. And then you've got residual connections. And that's really just because, we want gradient to flow effectively. Layer normalization, again, for gradient flow. So the bottom 2 are, just pre-existing in many modern neural networks beyond LLMs. But as language models and as neural nets get ridiculously deep, we need to come up with ways to enable gradient descent to kind of backpropagate smoothly through many, 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 many layers. Residual connections and normalization help with that. That's fine. We'll focus most of our attention on token mix. Now, the thing is, I showed you self-attention on the previous slide, but I've just changed my token mixer to something discrete over time, which very intentionally is the exact same figure as that spiking neuron, right? That unrolled acyclic computational graph of a single spiking neuron. Why is that? Because spiking neurons are token mixers as well. If I'm passing in Shrek at the first time instant, then Saw and Taylor with binoculars, all that information is being mixed. It's not being mixed very effectively because you kind of have that decay of information over time. You're forgetting, but it's still being mixed, right? So it is a token mixer, just maybe not a very powerful one. It's a cheap one, but it's not a powerful one, right? So how can we fix that? How can we use spiking neurons and recurrent neurons? So recurrent neurons just being a generalization of spiking neurons. How can we introduce recurrence as an alternative to self-attention, taking the power efficiency of and memory capacity of spiking neurons, along with boosting its performance to hopefully match self-attention somehow? To address this, let's address the challenge. First, figure out the challenges of recurrent neurons. One, backpropagation through time. Remember, every time I have an additional time step, that's one whole extra kind of column and an extra arrow that needs to backpropagate to do gradient descent on this graph. We're still relying on matrix vector multiplication, so we're just adding extra operations over time. And finally, perhaps most critically, poor long-range performance. That is, when you have a long sequence, you forget all the information at the start of your input. Let's address these one by one. Let's first figure out how to get around the backprop through time problem. I'll be a little bit arm's length about it, but with spiking neurons, they look something like this. Let's take, for example, of 3 input spikes of various amplitudes, and that causes a membrane potential fluctuation of various values. The way that I've represented it here is in this recursive form, where the next discrete voltage is a function of the previous voltage, right? And that is expensive because it's linearly, it grows linearly with complexity over time. But ultimately, I'm stuck with a for loop, and I can't process the next time step until I've kind of gone back. But there are ways that we can do this. You can sidestep the backdrop through time problem by removing nonlinearities through time. And in the way that recurrent neurons were first proposed back in like the 1980s, this term here had a nonlinearity applied to it, sigmoid or tan H, one or the other. And if you go into PyTorch now, that's the default. You're applying a nonlinearity through time. But if you remove nonlinearities through time, you can solve for any single one of these points just using an exponential function, right? I can say exp to the negative t over tau with some scaling factor, and that's suddenly log n complexity. Each of these exponentials needs to be treated separately. And so the log complexity comes by having to kind of go through an adder tree, like some sort of tree-like structure to sum everything up, but it's a parallel scan algorithm. The issue with removing nonlinearities, if the deep learning folk are here, would be, well, aren't you breaking the universal function approximation theorem? And the idea is that if you have a nonlinearity in your neural network, you can approximate any abstract function, right? As long as it's continuous, you can approximate, even if it's discrete, you can approximate it with a continuous function. And it turns out that that's not a massive issue. Like you can kind of sidestep this by saying, look, let me have my linear token mixer, which is just this guy, right? This is one neuron, it's linear through time. That's all well and good. But on either side of it, let's have a channel mixer that is nonlinear. And that channel mixer might be a dense operation, like a fully connected layer with some nonlinearity. So you're just pushing the nonlinearity somewhere else, somewhere where it doesn't scale linearly with time. So you maintain log n complexity. So what types of linear recurrence are there? And before I push forward, the introduction of a linear recurrence is also really good for gradient flow, because if you apply a sigmoid or a tan H, then you get vanishing gradients on either extreme of that nonlinearity, right? By its very definition. So you're actually helping gradient flow in doing this. Now, there are 2 modern types of linear recurrence that I've observed in the literature. 1, exponential moving averages, or just static decay. Exactly what you see here. Got this exponential decay of your hidden state of your neuron. 2, gating mechanisms that rely on this kind of data-dependent decay. So if instead of saying, my decay rate of my neuron is 50% or 0.5 or whatever it is, instead of saying that, you have another neural network that is modulating, that is changing the decay rate. You're kind of learning how rapidly information should decay. So this is kind of getting at that forget gate mechanism, right? And if you do that, it turns out that recurrent neurons become so much more powerful, right? Without having to increase complexity. You do have another linear layer, but that can happen in parallel to everything else that you're processing. So in doing that, the backdrop through time has gone from linear complexity to log n complexity. That's nice. Now we still have this reliance on vector matrix multiplication. So let me try and highlight this problem to you. With vanilla recurrent neural nets, in the way that they were classically formulated, let's say that we have a 3-neuron structure. Every one of those 3 neurons has its own hidden state, V1, V2, V3. Then the way that we would update that hidden state over time would be through this matrix multiplied by the previous time step hidden state, denoted by this 0 subscript, and we would add the new input at the next step. Again, in the 80s, you would wrap this term up in a nonlinearity, but I think I've convinced you that we don't need that nonlinearity. We just push that somewhere else. So if I was to express this equation in a vectorized form, then I have V1 equals W and bolded to represent a matrix. Let's now try and iterate to the next step. Let's advance the membrane potential by 1 time step. Now I'm going to go ahead and make this substitution and put this term into V1 here, right? So I end up with this, and if I expand this equation out, then I'm left with W squared. What's the issue with W squared? I'm taking the square of a matrix. I'm doing matrix-matrix multiplication, which scales cubically in complexity, right? So memory complexity is squared because you're storing a matrix. Computational complexity is n cubed. I'm sure that there's a bunch of fancy algorithms that have kind of been shown in the past 24 months that squash this down to an order of 2.38, but that's still polynomial, and that only applies for very corner cases, right? In general, what your computers are running is cubic complexity. That's bad. On the other hand, if I was to consider a spiking neural network, you no longer have that matrix, right? You no longer have that 3 by 3 matrix. It's just that every neuron has its own decay rate, represented by W here, right? And if W1 is 0.5, then that's what's going to give me exponential decay. If I have data-dependent decay, then this vector is going to be a function of another neural network, right? And that is what we do. But let's just kind of go through this case with a vector element-wise product, a Hadamard product. We're doing the exact same sequence of operations as before. This time, instead of a matrix-matrix mul, we're left with W squared, where W is now a vector. And here, if I add extra elements to W, what happens? That's just one extra multiplication. So we get linearly increasing complexity rather than cubic. Now, of course, the most obvious thing to say is, well, I've only got 3 values in this transition vector. Previously, with the RNN general case, I had a matrix. I had 3 by 3. So am I losing some sort of representational capacity? Am I losing the ability to express interesting and important information over time? You have 1/3 of the values, right? And that's just going to keep scaling. So sure, perhaps you do lose something, but let me try and convince you that it doesn't actually matter. If I assume that my transition matrix, W, is diagonalized using your favorite diagonalization method, SVD or whatever, then let's say that P is a matrix of eigenvectors. It's a matrix of your eigenvectors. D is your diagonal matrix represented by D of eigenvalues. P inverse is P inverse. And if I bring back those hidden state equations, then what I'm hoping to be able to convince you here is that when I take W squared is the term I cared about. W squared is what gave me cubic complexity in the full matrix case. Then that is effectively substituting out PDP inverse for W times W. I get this term, and I'm left with P inverse multiplied by P. What does that do? Identity cancels out. I'm left with D squared. Do we know what a diagonal matrix is multiplied by a diagonal matrix? That can effectively be treated by an element-wise product, right? You just take every element along your diagonal and just multiply it 1 by 1. That's it. It's just a Hadamard product. And so suddenly we go back to linear complexity. If I go to W cubed, if I iterate my time steps step by step into the future, P and P inverse stay the same. The only thing that changes is that index. And that is going to be fixed at linear complexity rather than cubic complexity, right? So that is to say that all these, and in practice, the other concern is that, Well, taking the inverse of a large matrix is expensive. Truth. What does the deep learning community do? What did we figure out? How did we figure out the way to get around it? We just replace it with another learnable matrix. So that is to say that P d squared Q does not, it no longer equals W squared. But in our world, that doesn't matter. If we have an additional set of learnable parameters, then we effectively are compensating the amount of representation that neural network can kind of express. So it's kind of like we've derived all of this to show you, hey, these things can work pretty well. Oh shit, but that P inverse is expensive, so let's just add something else that isn't expensive but still helps our neural network work. And welcome to deep learning. It is what it is. But it works, and that's really what's important. So what is P? We now say, in the spirit of approximations, let's treat P as a nonlinear channel mixer, right? P is a matrix. Let's just say that it's a fully connected layer and apply a nonlinearity to it. D squared, that's our linear token mixer. That's the only feature that's changing over time. That could be our spiking neuron. That could be our recurrent neuron with the element-wise vector transition matrix. And Q is another nonlinear channel mixer. And that kind of perfect, it's the exact same figure. This in the bottom left is the exact same figure as what I showed you before, where I said that we are able to preserve the universal function approximation theorem if we take nonlinearities and put them in non-time varying operators with linear operations only in time varying components. And then that way you're able to get the best of both worlds. You're not going to linear or cubic complexity, and you're still able to preserve universal function approximation theorem. So all of this fits really nicely together. So what could D be? Now, if D, my matrix of eigenvalues that are now represented by that is now represented by a vector, if you squash the diagonal matrix, if they are real values between 0 and 1, then you just get exponential decay. But it turns out that you can, I think the people that are very comfortable with matrix diagonalization will appreciate that if they are complex values, then you get oscillation, right? You can get oscillation. And what that should hopefully imply, though, or at least ring in your mind, is that if I have a long sequence, you can kind of bring information back periodically from the dead. So rather than just fading information over time, kind of lift up Shrek back out of the dead if that salient information is important. And so all of these things are really kind of working in tandem, right? I'm showing you benefits of long-range memory that accidentally arise by trying to address the vector matrix multiplication problems, right? They're all very much intertwined. So we've addressed that, and we partially addressed poor long-range performance as well, right? We did that via linear recurrence to avoid vanishing gradients. We did it by by using complex eigenvalues, which led to oscillatory state dynamics. But there's just a little bit more that we can do to milk the final 10% of performance. And what we've seen in the past with respect to long-range performance in recurrent neural nets, what I would effectively say are hacks, right? 3 hacks in deep learning to make them work, to make models learn or remember things over time. One came from LSTMs back in 95, 96 by our Lord and Savior Schmidhuber. He introduced this notion of control and forget gates. I'll talk about forget gates in more detail. Another is regularization. That is, your state matrix is kind of set to something initialized close to 1. So rather than having 0.5, where you get you're halving your stateful information at every step, if you set it to something close to 1 and bounded that, then you're able to preserve information pretty consistently. And finally, temporal residual connections, where you simply just push information into the future, right? Now, these are regularization, we do that. Residual connections over time, not super common, but I want to pay most attention to gating mechanisms, right? And so with forget gates, they kind of came about in 95, 96, and they did a really good job of enhancing RNN performance. But people have kind of forgotten about it because everyone's focused on self-attention, right? But if we bring forget gate back into the context of linear recurrence and put all of these tricks together, then turns out you're able to get really good performance. Now, people have forgotten what forget gates are, but if I take this single neuron, and give you a toy example, I take a single neuron, varying over time, and rather than using numbers, let's use some pretty colors so that the intuition is there. Let's say that I pass blue into one neuron, that goes at t equals 0, t equals 1, and then at t equals 1, I apply some yellow bit of information. But the thing is, this neuron doesn't expand in memory capacity. It's got one value as its state, and that's all there is. That means that blue and yellow need to kind of mix together, and you can't really isolate them out, right? You're left with this gross looking green-brown color, right? Think of that numerically. On the other hand, if you introduce forget gates, then the kind of power that you're equipped with is you can forget information if you don't need it, right? So let's say that my forget gate at one time step is 0 and at another time step is 1. Let's do the same toy experiment, right? We apply this blue bit of information. Now, some information multiplied by 0 is 0. We get rid of it. My forget gate has said that that blue bit of information is not something we need, right? And that's made space for something that is perhaps a little bit more important, that yellow bit of information. And that moves forward in time, and now I'm left with the thing that I care about. So intuitively speaking, that is what a forget gate is doing. And when I apply another neural network to determine the decay rate, that is the transition vector. Originally, it was a transition matrix that we collapsed down into a vector, which is now scaling of ON complexity, where n is time, or n is the number of neurons. Then if you determine that neural network if you determine that vector using another neural network, then you're effectively introducing a learnable forget gate parameter. And that is exactly what we've done. Another step that can be taken, and this is actually very much inspired by the brain. It's this idea that, the brain is organized, and we think that the visual cortex is organized into 6 various layers. The early layers are very interested in low-level features like edge detection, right? The deeper layers, they're more concerned with concepts, right? So, low brain regions are trying to find corners and edges. Higher brain regions are thinking, all right, so what is the association of all these edges together? Oh, that's a picture of Shrek, right? So you're coming up with more conceptual ideas. In the same vein, that's a spatial representation of what the visual cortex is doing. But there's also something similar going on over time, right? Early brain regions are kind of taking quick snapshots over time and leaving deeper brain regions to kind of stitch those brief snapshots over longer periods. So that is to say that early brain regions are forgetting things quickly in order to make space for something new, while deeper brain regions are kind of the mechanism that dictate how long I should remember something for. They're stitching all of these bits of information together. And we stole that idea and pushed it into our matmul-free model. Actually, everything I'm describing is all just like the backbone of the matrix multiply-free model. So if I separate my model into various blocks, then I would say that this kind of heuristic that we implemented was that the forget gate in the earliest block has some lower limit, denoted as gamma 1. The next block has its own lower limit, and so every block has its own unique independent lower limit. The thing is that these lower limits are derived to be monotonically increasing as you get deeper and deeper. What that means, the practical implication of that is that block 1 forgets information faster than block 3. Block 3, your deepest block, is going to be remembering information over a longer period of time, right? Remember that colorful example with blue and yellow? It just means that F1 can go down as low as 0. F3 might be a little bit closer to 1. So it's storing information. And so you're just biasing your model you're biasing different parts of your model to effectively do different tasks. The way that we implemented this in practice was super dumb, and it worked really well. We randomly initialized a bunch of values in our forget gate and then just kind of added, we did a cumulative sum, and that just guaranteed that, the deepest layer has the largest forget values. Meaning that it doesn't forget information as effectively. And we suddenly go into this regime where previously attention had too much information and RNNs or time-varying models didn't have enough information. But now, with that insufficient information, what I'm saying is that RNNs now store the correct information. They get rid of the shit that they don't need and store the information that they determine is useful. And all of these are really coming together to build something quite powerful. So all of these effectively been addressed. So let's talk parameters. Let's talk performance. We've gone ahead and worked with some various chips and hardware in order to actually verify that this model does work effectively. The bottom line is that on GPUs, the performance is marginally better than, the hardware level metrics of latency, energy consumption per token. All of that is marginally better than modern language models because the models that we're creating are really not tailored for GPUs. Ternary parameters, well, no, GPUs are kind of stuck with 16-bit values. Or recent architectures might go down to 4-bit floating point, but we're not using that. So we really got to come up with something highly customized in order to get this working effectively. So we've been working on our own hardware. This one over here is kind of like a crowdsourced chip that was developed in my ECE 110 through 10 class. And it's, for people that aren't into chip design, this is just a kind of like a microscopic render of what a chip looks like. And it's kind of beautiful. All of these blue lines are just, it looks like a city, right? It looks like a built-up city, but these blue lines are just metal wires that connect a bunch of transistors underneath. And so this was just a Hodgkin-Huxley, very simple digital neuron. It's designed in this class. But in order to do something functional, we need to scale up, right? We need fancier neurons, we need fancier implementations. So in order to get something rapidly working, we collaborated with Professor Dustin Richmond in the CSE department, and we put together this matmul-free model on an FPGA. And ultimately, we were able to get 23.8 tokens per second at 13 watts. What does that mean? How does the brain work? Humans, we read at approximately 5 to 15 tokens per second at 20 watts. So we're suddenly seeing that we're able to get a model that beats the brain's performance in a way, right? Granted, this model does have its own performance constraints outside of hardware, right? Can that model invent things? Can it talk shit to you in this presentation? Probably not that well, but it, compared to all of the self-attention transformer baselines, it's performing on par, and that's a nice thing. We still felt we could do better, right? FPGAs still have a lot of fat that could be trimmed. So what did we do? We have linked up with Intel, and they've got their own brain-inspired neuromorphic processor called Loihi. It's fabricated at the 7 nanometer node, and it's not like we designed this hardware by any means, but what Loihi's benefit is that it's an asynchronous chip, right? Microprocessors, as we currently know them, all have clocks. Everything is kind of clock gated. When you have data going in, nothing happens until the rising edge of a clock cycle. But what I've told you here is that, in spiking neural nets and in anything that with a sparse representation, you typically don't want to process anything if there's nothing new. And so if you have a whole heap of sparsity, your clocks are wasted, right? Your clock's going to be kind of going up and down while there's just idle information and nothing to do. And so that wastes a lot of dynamic power. And so this neuromorphic processor is really well suited for workloads that are sparse, matmul-free being one of them. Also because the matmul-free model is structured in a way that very much looks like a spiking neural net without that binarization of activations constraint. So we worked with Intel in order to get matmul-free compiled down to microcode and running on Loihi. And I'm going to show you some results of what all of that is now. And we're comparing the matmul-free model against what's called Transformer++, which is the open source baseline. Everyone kind of goes to it when there is an open source comparison. It's the backbone of a lot of, I guess, modern language models nowadays, in particular Llama, which is Meta's open source LLM. And we're comparing matmul-free, all sizes, so going up to 2.7 billion parameters, against 370 million, 1.3 billion, and 2.7 billion parameter Transformer++. So on the x-axis, we have sequence length. Now, for context, this 1024 is pretty small. DeepSeek R1 is more like 128,000 tokens long. Variants of Gemini have 1 million tokens. So that is kind of where the state of the art is. On the y-axis, we have throughput. We have throughput in terms of samples per second. So that's what we really want is a large number. Higher is better. And so with matmul-free, what we see is that we don't start beating Transformer++ until we go into the larger sequence length regime. And honestly, this curve, I could extrapolate it a bit, and then you could see that our model does better, but it doesn't feel good, right? We went through all that effort for this tiny little bit of improvement, and even down in the low sequence length regime, we kind of suck, right? So what's missing from this picture? Energy, right? We haven't accounted for the fact that Transformer++ is running on an A100 GPU, whereas matmul-free is running on an asynchronous accelerator. So in order to quantify that and capture energy into this picture, what I'm now going to show you is a more representative metric that is on the x-axis, joules per token. How much energy does it cost to generate one token, one sub-piece of a word? In that case, lower is better. We want less energy. On the y-axis, throughput per watt. How many words are generated per second given 1 watt of power? In that case, higher is better. We want more words generated given that 1 watt constraint. And what you're seeing is 2 green dots, which are the transformer plus baseline. This one is the 1.3 billion parameter model. This is a 2.7 billion parameter model. So that's represented by the diameter of the circles. This one is slightly larger than this one. And where does the MapMol3 model sit in relation to the transformer plus? We've got to zoom out quite a bit to get that. And we'll see the 2.7 billion parameter model here and the 1.3 billion parameter model here. So we're seeing much higher throughput, far less joules per token. That's really where we want to be. That 10x improvement is really kind of the dream here. But this isn't fully representative either, right? So what are we missing now? Remember, our model was ternary. The parameters were ternary. Transformer plus in our simulations for equivalent language modeling performance in terms of complexity and a bunch of other benchmarks, that's using the BrainFlow 16 numerical format. And so if we normalize for, skip forward in the animation, if we normalize for memory usage, then the transformer plus expands in size because they're using far more memory, using far more energy for equivalent performance, right? And so that is really where we need to kind of go with language modeling. If I can kind of even go further and show you real life demos of what these guys are doing, if I type in Python, llama, run, and I'm kind of biased it to give me this text that's kind of predetermined. Say, hi, I'm llama 3.2. We see this text being generated. That's all well and good. It's just tell it I'm just doing this purely for a benchmark. Nothing too interesting to see. But if I go to the next slide, and what I'm going to do is show you that text generation process again, but this time with energy profiling metrics. So what you're seeing here is idle power, but then the moment I hit run, you start seeing a bit of like actual dynamic power, something that is processing this workload. So yeah, we go from on an A100, is it an A100? I think I said it here. H100. Okay, so we're running on an H100. Power jumps from 200 watts to 300 watts with this real-time profiler. This time I'm going to show you the MapMol3 model on the right-hand side running on Loihi. So what do we have here? You're going to notice that not only is this ridiculously faster, but it's far more efficient, right? Total power in this case, the 2.7 billion parameter model, I think. Yep, 2.7 billion parameters, 20 watts at a speed that is 1.8 faster. So it's kind of, can't even compare the two, right? So what's nice is that, yeah, we successfully managed to shit on a lot of the models that are currently out there. And yeah, it's very rare for me to kind of say, oh, hell yeah, we just came up with some research that is meaningful and kind of competitive with OpenAI and what the work that everybody else is doing. So I don't know, it's probably the only time in my career that I've been claimed that we actually did something kind of useful. So with that being said, none of this work is possible without the absolute stars in my lab, in particular with the work that I've shown you. Ridger is the hero of all of this. He kind of led the Spike GPT and MapMol3 work. I would be nothing without Ridger. And yeah, a few references about all the work that I've described. On the top, our work, namely MapMol3, Spike neural nets, Spike GPT, and SNN Torch. And on the bottom is work from other labs whose shoulders we're effectively standing on in order to develop this MapMol3 model. So with that being said, amazing. I didn't go over time for the first time in my slide. I'm happy to answer any questions or just not answer any questions. Thank you.
Thank you, Jason, for the great talk. I have two quick questions.
Sure.
On one side, show that the power consumption of your proposed approach is like 13 watts. So do I understand correctly that 13 watts is the power consumption of your FPGA?
No, sorry, that was on Loihi too, the neuromorphic approach. So we did get 13 watts on the FPGA as well. And then when we ran it on Loihi 2, then it was something more like 20 watts of dynamic power. But then what was our idle power? There's very little idle power with Loihi 2. But yeah, so this is a much nicer number than the FPGA. The FPGA was slower, and also the static power was nowhere near as good.
But basically, the power consumption, that number is hardware dependent.
Oh, completely hardware dependent. So if I ran MapMol3 on a GPU, pretty much the same energy.
Yeah, sure. Second question is about you have this eigenvalue decomposition for your weighting matrix.
Yeah.
But I remember you mentioned that that matrix can also be data dependent.
Yes.
Right? So in that case, your eigenvector matrix P, or maybe the Q that you change later, and also the eigenvalues, they are all data dependent.
So D would be data dependent. Yeah, the eigenvalue, not the eigenvector.
Okay.
So D is data dependent, and so you're relying on, imagine X being your input data. X goes through a linear transformation followed by a nonlinearity. That modulates a vector of values. You have a vector of activations outside of that layer. Those become the coefficients to the complex, to your real and complex parts. That's treated as the eigenvalues.
I see. So sort of you are fixing the eigenspace, but you are only changing the weights.
So it transforms with the input. Yeah.
Okay. Yeah. Thank you.
No, all good now. And if there's no questions, then free cookies.
Anybody in the Zoom room, any questions? So back to last question, back to the general question, why not everybody using it?
Yeah.
So what's your long-term plan to actually adopt these in more problems?
I'm going to start threatening people. I'm going to take a gun and tell them, if you don't start using this, you will be sorry. No, the real answer is that this is hardware dependent, right? And a good analogy that I like to give is, if you come up with a new innovation that is 10x better, you need to convince people that the economics make sense, right? If I come up with a completely new way of doing computing or a completely new way of doing algorithms, will people adopt it? It's like saying someone has developed a new way to build train tracks, right? If I change the train tracks to be 6 inches closer, then I'm able to get something a lot faster. Now, if people are going to go around the world and tear out the railway tracks from every single place to get that slight improvement, probably not. Doesn't financially make sense. In this world, what are the train tracks? Microprocessors, a bunch of legacy Verilog code, a bunch of compiler frameworks, software stacks, CUDA, right? So if you have a 10x benefit, you also need to show that the economics of it makes sense. That's really the bottleneck of large-scale deployment. Some people are skeptical about ternary parameters. Some people say, you know what? I have a ton of compute. I have access to all of these huge server farms. I don't need energy efficiency when I have all of that. So to them, it doesn't necessarily make sense. But I think that there are some companies that are using, OpenAI included, I think they are using bits and pieces of what we've got just under wraps in a hybridized kind of form. Very philosophical answer. Yeah.
So you mentioned Spike GPT.
Yes.
So spiking version of GPT.
Yeah.
And you mentioned Wiki 2, the infrastructure for running spiking behavior.
Yeah.
So your Spike GPT is also running on Wiki 2.
So we started to do that, and then we developed Matmore 3, and that worked much better.